Morning, everyone. Thank you for coming out and waking up for this. Let's get started. So I'm Holly, and today I'm going to show you Ectype, which is a proof of concept for a new way of building and extending programming languages that I've been experimenting with for the last year or so. So to set the scene, when I started doing web dev about 15 years ago, PHP was in vogue and jQuery was everywhere. And there was no TypeScript, and even CoffeeScript was relatively new. So working in JavaScript itself was the norm. And we don't really do that today anymore. Why is that? Well, hopefully it's uncontroversial to say that generally we wish JavaScript were better. I don't want to rag on it too much because enough has been said about its flaws, but I do want to mention some key ones because they motivate the shape of the web dev landscape today. So the biggest one for a lot of us is types, as the industry has moved towards strongly statically typed languages. Untyped JavaScript with its unchecked runtime type errors has fallen out of favor. A lot of newer languages also offer more powerful data structures out of the box. I personally find myself wanting some types. And then JavaScript also famously has a lot of these weird footguns. We have unusual scoping behaviors with like var and function. And then we have these weird type behaviors with coercion and these different types of equality. And these have to stay in the language because it has to remain backwards compatible. So hopefully it's not presumptuous of me to say that almost everyone who has to work with JavaScript directly starts to want many of these things to change. And as adoption of Node meant more and more code was written in JavaScript, we reached a point where the demand for change started to justify a lot of effort. And so if you have a dissatisfaction with JavaScript and an ambition to change that, what do you build? Well, for the last decade, the answer to that has been languages that compile to JavaScript, or transpiling if you prefer. And this approach makes a lot of sense. You are completely free to come up with your own syntax, and then you can achieve literally anything because you are using code generation to target a Turing-complete language. And so these languages tend to work like this. You take code that's in your new syntax, and then you do some sort of static analysis on it, usually type checking. And then you take that checked code, and you transform it into JavaScript, which is the form where it can actually be run. And so we got a lot of languages that work this way. TypeScript is the biggest one, but the power and flexibility of this approach means that we have a lot of languages, some of which take very different directions from JavaScript. But during that same decade, while we've been building all these languages, something else has also been happening. JavaScript itself has also grown and matured. And so ES6 was the first big step. We got Latin const and arrow functions, which help us with these weird scoping behaviors. We got classes, so if you're coming from an OOP language, you don't have to know how prototypes work. And then we got things like generators and async await that just generally improve our quality of life. And we take these kinds of features for granted now, but they were big steps in making JavaScript more tolerable to work in. And this started to erode the advantage that these transpiled languages have. And so I started to ask, do we really need all of these new languages? You know, there is some overhead to them. Languages introduce a new syntax that you have to learn, and then you have to set up tooling like bundlers and source maps. And then we're putting all this effort into building these efficient JavaScript engines like V8, and then they end up running generated code anyway. But also in principle, JavaScript is a scripting language. So what happened to being able to just write JavaScript and then run it? And the JavaScript, like the transpiling to JavaScript approach brings so much to the table that generally we accept this trade-off. But I do think it's worth asking, what if JavaScript is enough? What can we achieve within JavaScript itself? So if we go back to this list of things that we want to change about JavaScript, we'll find that broadly we can divide them into additive and subtractive changes, right? Like we want to add types, we want to remove these weird behaviors. How can we achieve these changes without having to leave JavaScript? So for additive changes, we can use libraries. And this is already kind of the mindset of Lisps, where libraries are essentially DSLs that look and feel a lot like they're just native parts of the language. And this is tougher in more static languages with weaker reflection, but JavaScript is dynamic enough that it's quite easy to achieve this. And so here's an example of how we're already doing that. This is Zod, which is a popular library for validating data types. And you'll see that it introduces its own type syntax that mirrors JavaScript's own. So we've got these functions that represent objects and string and number. And the biggest drawback with Zod is that it only does checking at runtime. So if you want static type checking, you have to integrate it with TypeScript, and then we're back at square one. But actually, it's worse than that, because even if you do integrate it with TypeScript, then you end up with two syntaxes. You have a syntax for describing your runtime validators, and then one for your static types. And I've heard this called static dynamic biformity. It's the idea that in many strongly typed languages, you end up with two distinct syntaxes. And infamously, TypeScript's own type system is itself Turing complete. And since the point of this exercise is to see what we can achieve within just JavaScript, adding a second syntax is not ideal. But it does at least show us that it's possible. So what about constraining JavaScript? So if we want to constrain JavaScript, we can use a linter. And maybe we don't usually think of linters as constraining or reshaping a language, but we think of them as tools for code correctness or quality, but they do. So here's a simple example. This lint rule throws an error if the programmer uses the double equal instead of the triple equal, which we rarely do intentionally in JavaScript today. And so if we consider all programs that don't pass this linter to not be valid ones, for example, if we don't let them pass our CI or be merged into the trunk of our repo, then technically we are using in our org a slightly different version of JavaScript. And so even though this syntax is technically valid, it's valid syntax and it will run, we don't consider it to be a valid program. And so we can use this to effectively disable language features. But it goes further than that, because lint rules can apply to libraries too. So here's a lint rule that catches when you're using a React hook incorrectly. And using the linter, we've basically constrained the set of valid programs that use React. So here's an idea. If we have a library that's providing these language level type features like type annotations, and then we have a linter that's constraining the calls to that library to only the correct ones, we have a type checker. And so with this combination, we can sort of close the loop of static dynamic biformity that Zod leaves open, because now we have the full ability to add static typing to JavaScript from JavaScript itself. So we can add types with a library, and then we can constrain them with a linter. And so this is what the process would look like. Instead of analyzing a custom syntax in a new language and then transforming it to JavaScript, we take an extended syntax in our existing language, and then the code is runnable immediately. There's no transformation stage. And so conceptually, we can build a new language, while concretely, it lives entirely inside of JavaScript. So what would that look like? So to get an idea of this, let's look at a struct declaration in a strongly typed language like Go. So in Go, this is a type declaration, which for us becomes a variable declaration. And then struct is a keyword, which for us becomes a function call. And then we use an object literal to describe the shape of the struct. And then the types themselves would be constants. And then since JavaScript doesn't have an integer, we use the number type. And then the static analyzer would recognize this call to struct as part of a type declaration. And it would recognize point2d as a type, and then use that for type checking. And so this is the idea behind Ectype. It is a proof of concept language extension. I've never been really sure what to call it, built on top of JavaScript that uses this approach. And a quick note about the name Ectype. Ectype is a word that means the opposite of a prototype, and it's also a pun on ECMAScript and the fact that it adds types to JavaScript. So we've checked all the boxes for these terrible programmer naming cliches. So now I want to show you a quick demo. Ectype in action. Can everyone see that okay? Cool. So here we have a program that's written in Ectype. This is a web server that has one endpoint, distance, that calculates the distance between two 2D points. The entire source code of the server is on this left-hand pane here. And we'll see that if I mess with one of the types, I get a type error, right, which goes away when I fix it. And then if I want to know where a type comes from, I can control-click into it, and VS Code's own click to definition will take me there because it's all just JavaScript. It already understands it. And then since this is just JavaScript, whoops, I can just run it directly without building. And then we can hit the web server and get back a result. And then if I mess with the shape of the input data, we get back a friendly error message. But not only that, since it is just JavaScript, I can go into VS Code's own debugger, drop a breakpoint into it, and then run the file directly. No setup, this is just a JavaScript file open in VS Code. And then when we hit the endpoint, we'll trigger the breakpoint, and then we can introspect the values, just like it's a plain JavaScript file. So going back to this type syntax example, I want to show how we actually construct an instance of a type. So, whoops. Sorry, I forgot to hit save. There we go. So if we go back to this type syntax example, I want to show how we actually construct an instance of a type. So in many statically typed languages, a bare struct is not allowed to exist. The struct has to be tagged with its type, like point2d here. And so in Ectype, you do this using the from keyword, and then you provide the object literal. And so now we have static type coverage for point, and anywhere that this point is used, we'll get type coverage on its fields and what operations are valid on them. And just like in Go, if we use the wrong shape for our object literal, we get a type error, a static type error from our linter/static analyzer. And once again, this is technically valid JavaScript. It will run, but because it doesn't pass our linter, we don't consider it valid. And by the way, under the hood, this from function is implemented just as an identity function. It just passes the value straight through. And this is because the runtime is effectively trusting that the static analyzer has already taken care of type checking. So if a call to from exists in the code and it's being run, the assumption is that the value being passed through it has already been checked. So the runtime doesn't have to do anything. And so here's a quick overview of the data types in Ectype. In Ectype, the convention is for types and only types to begin with uppercase letters. So all the primitives are represented with constants. We have null, which is our unit type. And then null also shows up a lot because undefined is forbidden in Ectype. And then we have Boolean, number, and string, which are familiar. And then we also have unknown, which is the top type. It works kind of like unknown in TypeScript. And so all values are valid instances of unknown. And then we also have type, which is the type that represents all types themselves. And we'll come back to that later. And then for our compound types, they are declared using these keyword functions. So we have struct, which you saw earlier. We also have array, function, and tuple, which is backed by an array. And then we have variants. And so I want to talk a little bit more about variants because they're quite important to Ectype. So variants are an implementation of sum types based on Rust enums. And if you're not familiar with sum types, here is a criminally short explanation of how they work. A sum type is a data type where each instance has to be one of a fixed set of options called tags. So here an IP address can be either a v4 or a v6. And then each tag can also contain a data type within it. So in this case, string, which will contain the address itself. And then you can construct an instance of the sum type with a value that's wrapped in one of these tags. So here we see this is a string literal wrapped by v4. And then you can pattern match against that instance. And the match statement will allow you to unpack the value that's inside of this sum type instance. And then it will also check to make sure that you've covered all of the tags so that your match is exhaustive. And so in Ectype, variants use a similar syntax. We have an object where the keys are the tags and the values are the types. And then you construct them using of. We use of rather than from because it's not possible for a variant literal to exist in plain JavaScript, but this is mainly semantic. You don't have to worry about that. And then we match against it using match. And so this is still similar. The handlers or the match is described using an object where the keys are the tags. But unlike in Rust, each handler is a fully typed function. So if you missed the function syntax earlier, this describes a function that takes one parameter, a string, and then returns a null. And we have to return null because undefined is forbidden in Ectype. So you might notice, and the function body is mostly the same. And you might notice, if you're familiar with sum types, that this is a little bit redundant. The string doesn't actually need to be declared in the handler of the match because it should already be known in the shape of the variant. But actually later on, we'll see cases where this is not redundant. And then, just like in Rust, you can provide a wildcard handler to the match statement, and that will catch all of the tags that you didn't specify a handler for, and then your match will still be exhaustive. And variants are important to Ectype because errors are handled with variants. And so we expect errors to be returned in the form of a variant that contains a sum wrapped around the expected result, and then a none wrapped around null, which represents nothing. And so this is like the option type in Rust, or the maybe type in Haskell. And so here we have an example of a number option type. And then we can write a function that returns instances of this. So this is a function that might fail, a division function. And so if the divisor is 0, then we can't safely divide by 0, so we return none to represent failure. And then if it's safe, we return the result, but wrapped in sum. And then when we want to use the result from this function, we have to also handle the case where the division fails. And the goal in Ectype is to always try to handle errors in this way instead of throwing exceptions. And in fact, throw is disabled by the linter. So we have the groundwork of a language here, but we've also taken a rather unusual approach with some unique trade-offs. And so I think it's worth asking, what else can we get out of it? What does Ectype's unique approach tee us up for? So if we look again at this example, we'll see that this point2d serves as a name handle on the type that we've declared. But it is also a value that exists at runtime. And this means that in Ectype, types are values. And we can take this and run pretty far with it. So right off the bat, we get type validation for every type we declare just automatically. So in addition to from, every type provides this conform method. So like from, conform takes a value and asserts that it matches a type. So here we're trying to conform this mystery value to a 2D point. And maybe this value came from an HTTP request or user input at the terminal. In any case, we don't statically know what shape this value is. But unlike from, conform checks the type of this mystery value at runtime. And that's because conform is not an empty function. It is a runtime type checking function that we generated with the type when it was declared. And the trade-off of this is that since we can't be sure of the type statically, instead of a plain value, the value is wrapped in an option. And so maybe point would be a variant that looks like this. And then if you want to get at the validated value, you have to also handle the case where the mystery value is not a valid 2D point. And this, by the way, is how the friendly error message in the demo web app is achieved. So if we look at this segment of the code, we'll see that we still have static type coverage over the point. Like we can safely know what fields are valid and what their types are. And this is because conform kind of does the inverse of what from does. So rather than the runtime trusting that the static analyzer has taken care of type checking, now the static analyzer is trusting that the runtime will take care of type checking. And so this means that no matter where a value comes from and what we know about it, we always have a way of getting static guarantees on a type. So if the type of value is known statically, we use from, and if it's not, we use conform, and then we also have to handle the case where it's not valid. And this is one of the strengths of Ectype's approach. We get both static and runtime type checking from the same type declaration because that type exists both statically and at runtime. And then either way, there's always a region where we have coverage. And this means that Ectype's type system aims to be sound. I say aim because I have not proven anything yet, but basically whether code is statically checked or checked at runtime, unchecked type errors should be impossible. But conform actually goes a step further than that. In addition to validating unknown data types, or unknown data against known types, we can validate unknown data against unknown types. And to show you how this works, I want to talk about how generics are implemented in Ectype. So in Ectype, since types are values, the idiom is to try to resolve type matters in value space rather than introducing new type-specific syntax. So because of this, in Ectype, generics are just functions that take a type and then return a type. Right? And then by default, when we have a function that returns a type, we can't make any static guarantees about it because a function could have literally any arbitrary behavior inside of it. But generics are a very common pattern, so I would like someday for the type checker to be able to recognize when the user has done something like this, and then statically deduce the result of a call to a function like this, and then use it for static analysis. So under this hypothetical, it would look like this. The analyzer would recognize that num_pair here is a struct containing two numbers, and then we'd be able to make static guarantees against it. But unfortunately, this functionality doesn't yet exist in Ectype. So instead, num_pair is tagged by the analyzer as deferred. And this means that the type checker knows that it's a type, but it has no idea of the specifics. It doesn't know what fields it has, or actually if it's a struct at all. And so if you tried to call from on num_pair and make static guarantees against it, you would get an analysis error. And in the meantime, we can actually still keep our static guarantees using conform. And so here, if the result of conform is a sum wrapped around deferred. And when one of the options in a variant is deferred, the static analyzer will recognize what you're doing, and then when you try to pattern match against it, it will take the parameter of the first handler and use that to run a runtime type check against the incoming value. And this is why including the type in the handler is important. It's not actually always redundant. So here, this is the only place where that type is known. And so using this pattern, you can assert a value of an unknown type to be of a known one, and then also gracefully fail if this is not the case. And so when you do this, you do have to always provide a wildcard handler, because even if you do handle every case in the variant, it's possible for the incoming value to match the tag, but not the parameter in the handler. Right, so in this case, if maybe num_pair is indeed sum, but we described the struct incorrectly, we would have to fall back to the wildcard handler. And then once again, we get static type coverage in this region. So this is another case where the power of Ectype's approach really shines. The runtime can pick up the slack where the static checker is unable to, and we never lose type coverage. And this enables us to, we also don't ever have to leave JavaScript to do work on types. We don't need a separate syntax for this, which many other languages would require. And so there's one other feature that I want to show that highlights Ectype's static runtime handoff ability, and that's conditional types. So we've seen how we can constrain a value to a type, but what about constraining a type to a value or a set of values? So for example, the set of all positive numbers, or only strings that are valid email addresses. So in Ectype, we can do that with conditional types. So we use this keyword here, cond, and then the first parameter to it is the parent type. So here, all positive numbers are numbers. And so we base our conditional type off of number. And then anywhere that the type checker expects a number, a positive num will also be valid. And then the second parameter for this conditional is the JavaScript function expressing the condition and returning a Boolean, just in plain JavaScript. And this can be literally any valid Ectype expression, and it can even close around other values if you want it to. And many other languages do implement something like this, usually in the form of refinement types. But they would expect that you do this with a type-specific syntax. But here, we just get to use plain JavaScript. And actually, these languages that try to provide static guarantees against this, type checking in these languages can be incredibly difficult. And in fact, it's actually possible for type checking to become undecidable. But in Ectype, we can just cut the Gordian knot and say, just check it at runtime with conform. And then once again, we get static type coverage over this value, even though the validation happened at runtime. And then later on, we can even introduce static checking in half measures. So for example, maybe it's too difficult to cover this positive number function over all possible variables that could be passed into the condition. But we can cover easily the cases where we pass in a constant, like here. And so in cases like that, we can just warn the user, like, hey, in this specific set of conditions that you're trying to use here, we actually can provide you static type coverage. So conform is unnecessary. It will always succeed, and you can safely use from here and provide static guarantees. And then in all the other cases where our type checker still isn't smart enough and doesn't have coverage, we can just continue to tell the user to use conform, and it's the same business as usual. And so again, here's another case where this ability to hand off responsibility between the runtime and the analyzer really shines. And so languages that make strong distinctions between type space and value space, that have this strong static runtime biformity, would really struggle to do this. Because the realm of validation would be trapped either in the type space or the value space, and it's difficult for them to interact. And so there's one last feature that I want to talk about. There's the question of how does Ectype interop with the rest of the JavaScript ecosystem. And so there are two main features to Ectype that enable this. The first one is that in Ectype, all values are just plain JavaScript values. So if you look at a struct instance in JavaScript, if we were to print this out, we would see it's just a plain object. There's no additional tagging or metadata associated with it. And there's a couple exceptions to this. Variants don't exist in JavaScript, so they have to carry their functionality with them. And then functions also carry tags for their parameter and return types, because those can't be deduced at runtime. But neither of these adversely affect going from Ectype code to plain JavaScript. So what about the other way around? For that, we have this JS function. And this is kind of akin to Rust's unsafe. So the first parameter here is a callback where you can write any arbitrary JavaScript. And the linter and checker are just turned off completely. And then the second parameter is this type, and the result of the callback is just asserted blindly to be of that type. And so this is how we implement that HTTP server, even though no HTTP server library has been written in Ectype. So we wrap around the functionality that we want to expose, and then Ectype just understands it to be of that type, and then that's how we are able to call it. So ideally, you would only do this at the boundaries of the program, kind of like the functional core imperative shell paradigm, and then have as much of your actual code be written in Ectype. And of course, you can still call the Ectype type constructors inside of this JS body, so you can create valid variants and functions for use. So we have made a lot of trade-offs here, and I think it's important to acknowledge just what we've given up for this degree of flexibility. I think an obvious one is performance. Many types do indeed only need to exist statically, but in Ectype, they all exist in memory. And actually, since we're not doing any code generation, we can't even optimize them out. So I've not benchmarked Ectype, but it can't possibly be good for your performance to be spawning objects into memory that just don't need to be there. Another issue is verbosity. Since all values have to go through from and conform, Ectype code can get quite verbose, and the behavior around pattern matching is also somewhat verbose. And then lastly, as a language designer, we're limited in what syntax we can add by having to stay within the realm of valid JavaScript. And so there's a few things I wanted to add that I couldn't, like universal function call syntax and if expressions that I just wasn't able to add. So as for what's next, there are a lot of directions that this could go. My focus is on choosing a relatively small number of relatively powerful features to keep the surface of the language small, and I'm also hoping to make the behavior more ergonomic, especially around pattern matching. But outside of Ectype, I hope that the features that I've shown today inspire other language designers. Even if the combination of trade-offs that I've chosen here is rather specific, I think there's still value in a language that, for example, still offers code generation, but still incorporates this static dynamic handoff that I've shown. So as for where it is now, Ectype is in its very early stages, so all of the code that I've shown today does run, but that is about the extent of it. And so I don't think I need to warn anyone not to do this in production, because if you tried, I think you would hit bugs within minutes. But if that doesn't deter you, you can npm install Ectype today and try it out. And you can also find a current version of it at my GitLab repository here. And if you want to talk to me about it more, please feel free to email me about it. I would love to talk your ear off about it, or grab me in the hallway. And then I am looking for work, so if you're hiring. And that's it. Thank you.